Hello. Hello, welcome back to CS596. All right, so in our last lecture, we are done with logistic regression models, right? So I think I'm gonna release the homework, the assignments for logistic regression after the lecture today, because in that homework, I'm gonna have a question, have a task that will need to use the evaluation metrics that we will cover today. All right. And so today we're gonna talk about how to evaluate machine learning models. So this is actually a topic that we will not just talk about today. Later on, when we introduce more complex models, like deep neural network models, we will come back to this topic because the way we evaluate a model's performance actually determines how we're gonna allocate resources for training models, how much time and money we want to spend on a model. It's a very critical factor here. So the concepts that we will cover today include basically how we split the data sets into several folds, including the one used for training, one for testing, and for validation. And because so far we have introduced linear regression model and logistic regression models. And we primarily focus on the model that does classification tasks, okay? So which is what logistic regression does. So for the regression models, for the linear regression models, we actually in assignments we have mentioned we have a task for you to compute the residual sum of squares, okay? But the analysis for regression models, I would say it's more it's closer to the statistical analysis side, and when we interpret the behaviors or the statistical significance of predictors in a regression model, we would put more weight. We would put more weight on the interpretation, right? We will want to interpret the meanings of those parameters, and we would include like confidence intervals to describe the uncertainty or the probabilities of those parameters. But in classification model, as we will see today, we primarily focus on the performance of a model in terms of the predicting power, like how good the model is able to address the uncertainty in data, like the uncertainty in the labels, okay? And in the last section, we will talk about overfeeding and the ways to overcome, to deal with the overfeeding issue, okay? So this is not the first time that we talk about overfeeding in this class, because when we introduced the classification models in the first lecture, we showed several different types of decision boundaries, right? Some boundaries are really like just a simple line, but some sophisticated decision boundaries, they zigzag a lot to create a very complex curves. And we already mentioned that these are the representative this indicates the issue for overfitting. So now today we will more systematically talk about this issue, and more importantly, we're gonna know how do we deal with this potential issue, potential risk in the model. All right. Okay. So the splits of training sets, development sets, or this dev set is sometimes called validation sets. Training dev sets and testing set splits is the first step of setting up the machine learning models pipeline when you got a lot of data. Okay, so it's important to make a reasonable choice because sometimes the size of different sets will make a huge difference. So usually speaking, the training set should be the vast majority of data in our usage. Okay, we want to utilize as much as of the data as possible, but we still need to leave some space for the data examples to outside the training examples. Okay, for example, the green part in the middle, it is usually the smallest proportion of this split. It's called development sets or validation sets. Okay, or sometimes you call it a holdout cross validation. Okay, and the testing set is usually a little bit larger than the dev sets. Okay, so these threefold splits is kind of the standard operation to modern machine learning tasks, especially when the size of your data is very big. Say you have tens of thousands of images or hundreds of thousands of images or text data or whatever other kinds of data that you want to train your model on, then it makes sense to have such a train, dev, test split. Okay, so the usual workflow is that you keep training your model only on the training set. The purpose of the dev set, the smallest proportion, the green part here, is to see how your model performs. Or if you are training different models, it's used to select the models that performs best. Okay, and the test set is not used in the training stage. Okay, but the training set and the dev set, they are used in the training stage. Okay, the test set is only used after the training stage is done, when the optimal models are already selected, when the optimal parameters are already now fixed. So you can evaluate the final model on the test set. So in order to get an unbiased estimate. So we say unbiased because the test set is never seen in the training stage. It is kind of a more objective or unbiased estimates for the model. Okay, that is the usual practice. Okay, and in terms of the number of proportions, and when the data is small, for example, you only have hundreds or a few thousands or even 10,000 of some examples. Usually, because the data is small, which means the model would not be that complex, then you probably will not need the dev sets in the training stage. Okay, you only use the, for example, 70% as the training, and the 30% will be kept as the test set. It's never seen during the training stage. Okay, so one reason is that because your data is small. So if you only take 10% out as your, for example, as the validation or as the development sets, that's performance report from the 10% of a very small data set will not be a reliable resource of information, right? Because the data is already small. And if you only take 10% out, those 10% may not be representative at all, okay? But it's, I would say it's very depends on the actual situation, actual data. Okay, sometimes it's also acceptable if you would insist to have some depth sets. Okay, because some data may not be that randomly distributed. It may not be that noisy. Okay, and in another case, when our data is big, okay, for instance, we have 1 million data points. Okay, then in those cases, we usually have a very small proportion of depth set and test sets in terms of percentage. Okay, because 1% of a 1 million data points is already 10,000 data points. Okay, which in terms of abstract volume, it's not a small number, but in terms of percentage, it's quite small. All right, and it could be even smaller. Okay, depending on how many data sets you have. Okay, so these are all very practical choices, but the basic principle is that we use the majority to train the model. Okay, all right. So talking about the splits between train and testing distribution, we inevitably face the problem of the mismatch. Okay, because a lot of the application scenarios for modern machine learning based applications are using quite different training data sets versus testing sets. Because, for example, we're going to build some apps that can predict the species of fish images, right? It's a simple image classification task. We can collect our own training data sets, okay? But the training data sets that we collect in the training stage, it can be cleaned and processed with very scientific style, with very reasonable style, so that all those images are pretty much very user-friendly, model-friendly and very clean. But after the models are trained, if we're gonna release that as a product, then the actual input from the users, like the images uploaded from users by the phone images or by web camera images, those can be very noisy. Okay, the input can be very blurred, for example, very low quality, can be incomplete. So there's all kinds of unpredictable or much less predictable scenarios the models don't ever seen before. Yeah, so this problem is inevitable, somewhat inevitable, because we can never predict the unknown or wild data, right? But what we can do, I see the question. The depth set is used to report the performance of the model being trained during a training stage. So you can think of the training stage as a running for loop. So within the for loop, we are within each cycle, we are feeding some mini batches of data to the model, and the model get updated. So maybe after 1,000 cycles or 100 cycles, we want to have a peek of what the model looks like. So we're gonna use that little depth set to apply that model on the very small data set, and let's report the performance of the model in terms of a bunch of metrics like accuracy, like recall, like F1 score, and so on, and the loss, right? So we're gonna print those performance from the data sets as a indicator of how the model performs. Okay? So it's not used to train. It's not used to update the parameters in model, but it's still used in the training stage. Okay, it's not directly used to update the parameters, but it's used to report the performance. Yeah. All right. So facing this uncertainty in data, we basically gonna what we're gonna the best practice is to make sure that the dev sets are as close to test sets as possible. The ideal condition, the ideal situation is that they are from the same distribution, but we know that this is not necessarily like doable, because the testing sets are not like enumeratable. Like we cannot enumerate all possible scenarios. Okay, but what we can do is to make the dev set as close to test set as possible. Okay. So if in the case we cannot have a test set, so in that case, we totally depend on our performance. The report of the performance totally depends on the dev set. Okay, so that causes an issue of overfitting to dev set. Okay, so about overfitting, we're gonna have it covered later in this lecture. Okay. All right, now let's have a scheme of the regression models again. So a little bit review of the regression model. So the training set contains a bunch of training examples that comes with the feature xi and yi, right? So yi is a real number. It is a continuous number. It is not categorical. So that's why we call it regression. And the training sets, it's a smaller set of examples, right? But it has the same organization. It has the same structure with xj and yj, okay? So if we are interested about the performance of the model on one single example, right, we can use the L1 error, which is the absolute difference between the predicted value y hat and y, right? That's just an absolute difference. Or we can use L2, and this L2 is just the difference raised to the power of 2, okay, which is also the basis for the mean square error, right? It's just the error raised to the power of 2, okay? It's just the square of errors. So this L2 is just a fancier name for this square error, okay? So of course we want the errors to be small, right? A good model means the difference between the prediction and the actual value is smaller. So we want these errors to be small. These are the negative indicators of the model's performance. And in terms of the whole testing set performance, then we can use the average L2, L1 or L2 error, which mean the average L2 is just the mean square errors that we use for training the model, okay? And sometimes we can also include the variance of the errors, okay? So I have just one slide for the regression model. As I said, there are tons of details about how to interpret a regression model, okay, which is not the focus of our class today. So we're gonna proceed on to the classification models, which involves categorical variables. But this L2 error is something we want to keep in our mind, because this term is used a lot when we later on define the technique for overcoming the overfeeding problems. Okay. Alrighty. So let's look at the classification model. Okay. It's of course different from a regression model. So let's simply use the binary classification, which is the simplest case, right? And we already know about the logistic regression model. Okay, what this model do is to use the linear combination between the feature and our parameters, and feed the combination into a sigmoid function. The output of the sigmoid function is the probability of that data points belong to class 1. All right, so this is the y hats, the prediction. So when we make predictions, we use the middle points of the probability as a threshold. Okay, so we basically can visualize the results of the prediction, right? So we place the threshold in the middle here. So y hat equals 0.5. On the right, it's the everything to the right are the data points that are predicted to be y hat equals 1. Okay, and every data points on the left, they are those data points that are predicted to be 0. Okay, and what are the colors of the data points? The colors are the ground truth. Okay, and all the data points are in our training state, are in our training sets. Okay, these are the training data points. So the green one, the green data points are those data points whose actual labels are 1, while the greenish data points are those whose actual labels are 0. All right, so we can already notice that the model is not perfect because it's made misclassifications. Right, there are 2 points that are actually 0, but they got predicted to be 1. Right, they are on the right, and there's one actual positive example that has y equals 1. It is misclassified as y equals 0. Okay, these are all very often, but it's okay. We can tolerate these misclassifications. And the thing is, how do we use these results to come up with some metrics to tell how good the current model is, right? All right. So
can I ask a question? Does this data already looks a little bit trained, right? Because there's a lot of the green guys close to the 1, right? And so would this be something that we should expect to see sometimes, or is this something that generally only happens after training?
yeah, it's generally after train, because
okay, thanks.
If the model is not trained at all, then the model will give random guesses, right? The most reasonable way to expect a random model is just random guess. So it could be scrambled around. All the greens, all the grays are scrambled around. So this is definitely some models we have already trained, okay? And our purpose here is to use the outputs of this model to come up with some quantitative metrics that tells us how good the model is. Okay, so what we're gonna do is to draw something called a confusion matrix. All right, in this case, it's a binary classification. So what we're gonna do is to draw a 2x2 matrix, 2x2 grid. So the vertical, so the first row and the second row, the first row contains all the data points that are actually positive, which means they have the actual positive label. And the second row are the actual negative data points. While if we look at the two columns, then the first column is where we put the data points that are predicting, that have the negative prediction, while the second column has are for the data points with positive prediction that are predicted to be positive. Okay, so that you see the difference. We have two dimensions, right? The row dimension are using the ground truth, but the column dimensions are the separation using the predictions. Okay, so in that way, we basically can split all the data points into these 4 sections or 4 regions. Okay, so for instance, there are 12 data points that are actually positive, and they also have the positive predictions. While in this third region, we have 11 negative data points that are predicted to be negative. Okay, so these two categories, these two regions, the upper right and the lower left, these two regions are the correct predictions that we wish to see, right? Because positives are predicted to be positive, negatives are predicted to be negatives. Those are the correct ones. And because we already see the misclassification in the previous page, we will find that, okay, there's one positive number, positive data points that are misclassified, that are mispredicted as negative. Okay, so it's the first column, it's in the first row, but it appears in the first column. Okay, and on the other side, there are 2 negative labels that are mispredicted as positive. Okay, they're supposed to be on the first column, but now they're in the second column. All right, so these 2 misplaced data points, okay, are something that we will use to compute about the performance of the model. All right, so we're gonna define some numbers, define some quantities using this confusion matrix. The first one is called true positive. Okay, so as this name indicates, it refers to this region. It's those yes examples that are correctly predicted as yes. Okay, we call it, for abbreviation, we use the letter TP to indicate true positive. All right, and third region, true negative. Okay, which is also straightforward, right? The negative examples that are correctly identified as negative. Okay, so now let's go to the false positive, which is the fourth region here, right? They are predicted to be positive, but actually they are not. Okay, the no examples that are incorrectly identified as yes, so that's why we call they are false positive. Okay, so some maybe in statistical books we will call it a false alarm. Okay, it's a false positive. Okay, we use FP to indicate this quantity. Lastly, the second region is called false negative, right? It is supposed to be a positive prediction, but now it's a negative prediction. Okay, all these names are pretty much, I think it's very reasonable names, right? So having those 4 regions counted, now we have 4 numbers, right? All right, so given these 4 numbers, we can do some further calculation. For example, when we talk about the accuracy of the model, right? The accuracy is basically computed in this way. Okay, so again, compared to the previous table, right? We only have 4 columns. If we add the true positive plus the false negative, okay, we have the total number of true points, right? And the n is the total number of negative examples. Okay, so these are just simple summations of the previous columns. All right. So what we're gonna do with accuracy is simply the ratio of the true positive and the true negative among all data points, because t plus n is the number of all data points. T plus n is just the number, total number, which is the number of these four regions, right? So if we take only the correct region out, and its proportion is the so-called accuracy rate, or just the accuracy, right? So it's a simple fraction of correct predictions. I think this is a very straightforward quantity, right? And people's, like most of us, the intuition is to know about the accuracy, because we want to know how many accurate predictions the models has made. All right.
Does the inaccuracy also have, is that like a term as well? So like the false negatives plus the false positives over the total number, or is that?
Yeah, if you use 1 minus accuracy.
Oh, okay. Yeah, that's a good way to get it too.
Yeah. That'll basically the opposite of accuracy. I think in most papers we'll call it error rates. Yeah, those are the proportion of errors the model has made.
Thank you.
Okay, so yeah, other than the accuracy and the error rates, we should consider some other quantities. So for instance, this one, precision. So precision is defined on top of those positive predictions, the second column, okay? So the second columns are the number of positive predictions regardless of its actual labels, okay? So if we look at this column, it has 12 plus 2, which is 14 positive predictions in total. And we know that only 12 of it, among these 14 positive predictions, 12 of it is a precise prediction, is an accurate prediction. So that's why the ratio of the correct positive predictions among all positive predictions is called precision. Okay, this quantity is also a useful measurement of metrics, because it's basically evaluates the quality of positive predictions, right? So you can think of it that way. If a model tend to make positive predictions, right? If a model keeps make positive predictions, then it is likely that it will pick up all the actual positive data points, right? But the precision may not be that high, right? Because the model is not is too bold in making positive predictions. Okay, it hopes to the model, if the model hopes to not to leave the any positive numbers behind, then it may not be that precise in its predictions. Okay, so that's prediction. Now we're gonna look at a second quantity, which is recall. Okay, we should look at these two quantities at the same time. Okay, recall on the other side. Okay, it's defined over the first row. Okay, so it's basically the ratio of this true positive, the first region, over the summation of the first row. Okay, it's true positive plus false negative. Okay, so this true positive plus false negative is just the number of all positive examples. Okay, and this recall, you can think of it as the proportion among the proportion of correct predictions among all positive ones, right? So the recall is high if we leave no positive examples behind. If we tend to pick up as many positive examples as possible. Okay, so the recall and the precision, they are two different concepts. Sometimes when we want to improve the recalls, right? So we want to pick up as many positive examples in the data as possible, then we are going to increase the recall. But the price could be that we are making too many positive predictions. That's among our positive predictions, some negative examples are also picked up, which would probably result in a very low precision, right? So we are trying too hard in making positive predictions, okay? Because we don't want to leave any positive examples behind. But a side effect is that we are also picking up some negative examples. Okay, the false positive rate could be high and the precision could be low. So there's often a trade-off between this recall and the precision. Okay. All right.
Professor?
Yes.
So is precision, oh my gosh, I can't say it. Precision and recall, is it always in terms of the positive side, like positive prediction?
That's basically true. Yeah, that's how we define those concepts.
Okay.
Yeah, but if you flip around the negative versus the positive labels, you can also define the precision and the recalls in terms of the negative examples. I think it's totally symmetric.
Okay.
Yeah. All right. Okay. So other than precision and recall, for example, here we have specificity. That is the proportion of actual negatives that are correctly identified as negative. So you can think of it as a negative version for the recall, right? So this one, in terms of the name, specificity is not used as much as often as precision and recall. So precision and recall, I would say these are the most commonly reported metrics in academic papers. Okay, but as I said, I think in this case, the positive versus negative examples, they are totally symmetric. So if you flip around the concepts, you can also think of specificity as a way to describe the recall for negative examples. Okay. All right. So using the precision and recalls and these numbers, true positive, false negative, and false positive, we are able to define a more robust evaluation of the model, which is called F1 score, or sometimes we call it F score or F measure. Okay, so we can basically take precision recall, use precision times recall times 2. Divided by the summation of precision and recall. Okay, and if you, it's basically the basically this quantity. Okay, and it's basically it's average between precision and recall. So because there's always such a trade-off when precision is high, the recall is not necessarily high. So if we want one number to indicate the performance of a model in a more balanced way, then we can take the middle between the two, right? Take the middle between the precision and recall, so that it can be a more comprehensive summary of how good the model is. Okay, so F1 is definitely one of the most commonly used scores when we report the performance of models. Alrighty. So other than the numbers, we will also use some curves to describe the behavior of models. Okay, so this ROC curve is something that we can obtain from the plots of recall versus the false positive rates. Okay, false positive is the rate of false positive among all negative numbers. Okay, so if you plot the curve, it'll be like this, and the larger area there is under the curve on the ROC curve means better performance. Okay, so it means that we achieve a very high recall without losing too much false positive rates. Okay, without increasing the false positive rate too much. So this is another way to represent the trade-off between recall and precision, because when you try to increase the recall, it sometimes inevitably increase the false positive rates. Okay, because you want to recall as many positive numbers as possible, then you are being bold, right? Being bold, one consequence is that you are making false positive predictions. So the curve represents the trade-off between the two, but the one that has the largest area under the curve is the one that we the best model can have. All right, that's ROC curve, and we have just gone through the example for a binary classification case. So in a lot of the actual models, we have multiple classes, right? We have, for example, 3 classes, cat, dog, rabbit, 3 animals, right? So we can still use the matrix to represent the results. So in this case, we said we can find that 5 cats are predicted as cats, right? Maybe 3 cats are predicted as dog, right? 3 dogs are predicted as dog, but 2 dogs are predicted as cat. So those in the diagonal lines are the correct answers we want to have, right? But we can basically use the same technique to describe the performance of the model in terms of one class. For example, when we care about the cat class, we can basically combine the other 2 dog and rabbit columns into one column, right? We can combine the dog and the rabbit rows into one rows. Okay, so in this way, we can have only a cat versus non-cats what's it called? It's a cat versus non-cat model, right? So we can use the series of metrics defined previously to report the performance on this particular cats category. Okay, and we can do that for the dog, for the rabbit as well. Okay. All right. So yeah, the precision and recall trade-off, let's go through it again. Okay, so for example, different tasks may place different preferences over either recall or either precision. Okay, so probably when we want to define when we do diagnosis in the hospital, right? Before we want to make a surgery, like to remove a tumor in a head, right, in a patient's head. So when doing those models, probably the precision is more weighted than the recall, because we don't want to make a false positive. We don't want to make the false alarm, right? Because the price is going to be really big, right? And it really depends on the situations, right? It depends on how much price we can afford in making wrong predictions. All right, okay. So that's pretty much for how to evaluate classification models. So next, let's talk about the issue for overfitting and regularization techniques. All right. The issue for overfitting usually happen when the model fits the data too well. Okay, so because the parameters almost fit the training data perfectly, so they would sometimes fail to fit new data or to fit the unseen data. Okay, and we would say that if the data is overfitted, then if the model has overfitting issue, then it basically cannot explain the general patterns. It's just remembering the idiosyncrasies in data. Okay, so if the main cause, think about the main cause for having a model overfitted. It's usually we can conclude that maybe we have too many parameters. Okay, or the training data is not a big one. So that also actually reveals some rule of thumb. If we have a small data, then we probably want to use a simple model. Right? The complex models are only useful when you have that sufficient amount of data. Okay, it's basically these are two correlated quantities. Okay, so it's a bit like the Occam's razors rule. So it's like if you can explain this small data with fewer parameters, so why bother using a lot of more parameters? Okay, because the fewer parameters can already explain the general patterns. Okay. Alrighty, so now let's look at the example of regression models. Okay, if we this regression is not a linear regression because we use the quadratic terms of the feature inside, right? So if we have one quadratic terms, maybe the curves may look like this, right? To fit the triangle data points. Okay, so we can think of it as good model, right? So what about we use the cubic term and the higher order polynomial terms, right? Which means the models will fit better to the data points and may go through each data points in the training set exactly, okay, as they are. So this is something that we would call overfitting. Okay, yeah. So as compared to this good fitting and good model and overfitting, we will may have a third option, a third consequence, which is a underfitting. Okay, so the underfitting is the opposite of overfitting because we use too few parameters when we could have used more, when we can have the option to use more. Okay. All right, so in the classification model case, we are actually drawing decision boundaries. Okay, so these plots I think I have shown in the previous lecture. So sometimes the decision boundary that is too simple is not what we want, but those too sophisticated examples are not what we want either, right? We want something that's in between. Okay? But it's hard to tell. It's hard to tell which ones are definitely which one are the best decision boundary. Okay, so what we can do is to use some technique in the training stage to avoid such a overfitting issue. Okay, and of course it is by design we can use fewer parameters. That is to say, we use fewer features and we use simpler models. Okay, so these principle basically can be approved if our model is simple, then we can conduct a process called feature selection, right? For example, in the backward style, we start with all the features we have and we train a model, and then we remove one feature and train a second model, and remove two features, train a third model, and we compare the performance of all the models. And the forward style is the other way around. We start with one feature and gradually adding features into the model. Okay, and the process can be very lengthy because it take a long time sometimes when you have a lot of features. Yeah, but it's worth trying if you have not that many features. Okay, and in deep neural network models, say we have inputs in the form of images, videos, long, large body of text, right? So in those cases, audios, for example, in those cases, when the features are not single features, the features are dense vector features, then we're gonna use some different ways, okay? Because there's no ways to manually handle those features. So sometimes we want to stop the gradient descent process early, because the gradient descent is to find the points that the loss has the minimal value, okay? And around those regions, the models are fit the data very well. Okay, but we know that sometimes when you fit the data too well, it's not a good thing. It could be an overfitting. So the one straightforward technique is to not go that far. Okay, we can stop the gradient descent like at earlier points. Okay, we should stop as soon as the performance on the depth sets drops. Okay, so we are training our model on the training sets, and we can probably evaluate the performance on depth sets every 100 steps. Maybe when the depth sets tells that, okay, the model the performance is not that good now. Yeah, so the threshold is not a fixed number here. Okay, so it's basically if you remember the splits between training sets and depth sets. So depth set is a very small set here, while training set is a pretty big one. So for example, every 100 iterations, we're training a model M, right? Every 100 iterations, we take the M, apply to depth sets, and report the performance, for example, accuracy. Okay, maybe in the 100 iteration, the accuracy is 75%, and 200 iterations later, the accuracy on the dev set says 75.5. Okay? And we'll keep this running until some point, for example, when we hit 1,800 iterations. Let's check the accuracy on the dev set again. It could reach 75.4. Okay. Because compared to these value, it drops. Okay, and that is probably an indicator of overfitting. The model is overfitting to the training set, and then the performance on the dev set is dropping. So this 1,800 iteration is probably the point that we want to quit, want to stop training. So this is a usual technique that we can use when training a model, and there's no hard threshold. We are only compare the performance with the historical information here. Okay, we are compare the current performance with all the historical information here. Whenever the performance drops, then we will stop the training. Okay, so that is the so the M is a model. The M is a model.
Professor, quick question.
Yeah.
When the performance drops, we need to stop there or one step before that. Let's say it drops on 1800, so we'll go for 1700. That's one.
Mm-hmm.
Or which one we need to select?
I didn't hear you very clearly. Did you? Are you talking about how much the performance drops will decide whether we stop or not?
No, I'm asking when it drops, that level we stop, or we need to go one back, stopping and but selecting one level back.
Yeah. I get it. So I think it's a minor issue. So we usually when we train a model, we usually keep the checkpoint. We save two checkpoints every 100 iteration or so. Like we can, for example, we can set the program so that whenever we check the accuracy once, we will save two checkpoints. Okay, so basically, I think it's okay if we use the checkpoint at this point, even though it's a little bit off. But of course, if we are pursuing the best performance, we can go one step before. Okay.
Okay.
Yeah, those information in nowadays the frameworks they provide a very convenient way to trace back in the checkpoints.
Oh, thank you.
Yeah. Yeah, that's the early stopping technique. All right. So the one that we're gonna introduce today is called regularization term. Okay, so it's a very often used method actually in all kinds of different models. All right. So the general principle is to restrict the magnitude of parameters. Okay, we want the parameters don't grow too much to be. We don't want the models. We don't want the parameters, the magnitude of parameters to grow too much. Okay, because when the parameters have large values, which means we are placing a lot of weights on those features, and which means we are emphasizing the training data too much. Okay, so if we don't want to use that many information in the training data sets, then one way is to give some punishment to those parameters that has very large magnitude. Okay, we want to set a limit to how large the parameters can be, and the advantage of using such a technique is that we actually don't need a lot of prior knowledge about the features, right? We don't need to know about what kind of features we're using. We just set a limit to how large those parameters can be. So let's look at the method. The idea is to not minimizing the cost function, because previously in logistic regression or linear regression, we define a cost function using either mean square error or the cost function for logistic regression, right? And then we were actually minimize the cost, right? We use gradient descent to minimize the cost. The cost function is applied to the model and the data. Okay, so these terms within, you can think of it, they are the input to the cost function, right? The cost function takes the model parameter and the data as input. But now we need to add some additional terms. We now to not just to minimize the cost, but we also want to minimize the complexity of the model. Okay, and this complexity of the model can be quantified. We can use the magnitudes of parameters to quantify this complexity, model complexity. So what we do in practice is to use the L2 regularization term. Remember the L2, right? We use L2 error when we to measure the distance between the error rates between the outputs of a regression model and the actual label. But now the L2 is applied is not the one applied to the prediction outputs, but it's applied to the parameters. We can use the L2 regularization term on the parameters, on the W's. Okay, it's just the 2-degree norm. It's the Euclidean norm in with a degree of 2. Okay, so it's basically given the W. W is a vector. Okay, it has, for example, n parameters. It's a W. It's an n-dimensional vector. So we will take the square of each elements or each dimensions in that parameter and sum up all the squares. So these summation will be the L2 regularization term. And these summation also represents how complex the model is. And we assume that the larger those summation of squares, the more complex the model is. Okay, so we don't want the model to be complex. So, which means we want to minimize we also want to minimize the L2 norms. Okay, so having those L2 norms, L2 regularization terms defined, we can put it into the cost function. In the case for linear regression, right? The cost function, the old cost function, original one looks like this. It's the mean square error. Now we plot something new, okay? So this is a dot product. Remember, the dot product is just another way of showing the previous sum of squares, okay? So we are making the dot product between W and itself. The result is the sum of squares for all the elements in that vector. And we are also placing some hyperparameters like lambda and also a normalization term divided by 2n. Okay, the lambda is important here because it controls the strength of regularization. Okay, because we want to control the degree to which we want to regularize the function, the models, because we don't want to set a too hard limits. We don't want to set a constraint that's too strong. In that case, the model will never learn. Okay, the parameters will never grow. So the lambda is something we can use, we can choose. Okay, we can tune with different values. Stronger lambda means we want to place very strong regularization we want to limit to the magnitudes. And when lambda is 0, then we are now placing no L2 regularization at all, right? So when lambda is 0, then we're running under the risk of overfitting. Okay. So if lambda is too much, then it's probably underfitting because the parameters will not grow significantly. All right, then if you take a look of this new cost function and we take the derivatives of this cost function with respect to the parameter w's here, then with particular this term, the derivative of this term with respect to w will become this one. Okay, and if we plug in into the gradient descent formula, the parameters will be updated by alpha times the gradients, right? And the alpha is distributed into these two terms. Okay, so if we look at this term, it has w, right? It can be combined with a w here, so it becomes this term. Okay, so we can notice that the w is 1 minus alpha times lambda divided by n, and it is smaller than 1. Okay, which means our w is smaller than the values without L2 regularization. Okay, and the larger lambda means we will put more penalty to w, and the w will be smaller values, which is exactly what we need. All right, and that also applies to the cost function of logistic regression. Say this is a cost function for logistic regression, the original one, right? But the L2 is in the same form. It's just the sum of squares, right? And if we take the derivatives of it, we'll have the same thing, right? The derivatives of the cost function will be the same part, and this one can be combined to w, and this is the new value for w, which is smaller than 1, right? And the lambda can be tuned if we want the L2 to be, if we want the regularization effect to be small, then we should use smaller lambda. All right, so putting all this together, we are pretty much done with the L2 normalization. Okay, so if we look at the outcome, then if we have some regularization, then the magnitudes of the parameters will be limited. Okay, which means the models will be less complex. Okay, which also means it's less likely to overfit it. Okay, so but when lambda is extremely large, then the w's becomes too small, right? If the w's become too small, then it's hard to observe non-linearities here, right? Those higher order terms, they are almost invisible. So the lines will be almost a straight line. Okay, so there's a subtle trade-off here. We don't want the lambda to be too high or too low, right? So it's very tricky, but it's worth trying. Sometimes you will have some amazing effects on the model performances. And in this link, I hope this link still works, but it's a really cool visualization of how you can tune different lambda as a L2 regularization, and you can observe that the model's performance can be significantly influenced by the lambda you chose. All right, so yeah, that's pretty much for today's lecture. We'll talk about training, testing, validation splits. We'll talk about the performance metrics, precision recall and F1, and overfitting and the regularization, L2 regularization. Okay, so we will keep talking about overfitting and the regularization term. We will have more other techniques involved in the future when we introduce neural networks. And yeah, that's pretty much for the lecture today. Any questions? No question. Good. Okay, so I think there is a quiz today for the evaluation metrics, and I will also release the assignments for logistic regression later tonight. And I will end the recording now.